Right now, as you watch this, approximately 7 billion atoms are working in perfect coordination to create the experience you call you. Each atom in your body is 99.999999996% empty space. If you removed all that emptiness and compressed just the atomic nuclei, your entire body would fit into a space smaller than a grain of salt. Yet somehow, this mostly empty arrangement of particles is capable of contemplating the entire universe. This isn't philosophy, this is physics. And what you're about to discover will fundamentally alter how you perceive reality itself. The human brain wasn't designed to comprehend cosmic scale. Evolution shaped our minds to track predators across savannas, to judge distances we could throw a spear, to navigate territories we could walk in a day. We're exquisitely calibrated for the middle realm, what scientists call the mesoscopic world. Anything smaller than a millimeter or larger than a mountain becomes abstract, reduced to numbers that our pattern recognition systems can't truly grasp. But here's what makes this moment in history unprecedented. For the first time in 4 billion years of life on Earth, a species has developed tools precise enough to measure everything from the smallest quantum fluctuations to the edge of the observable universe. And when you map that full spectrum, when you truly visualize the scale, something remarkable happens in your neural architecture. Let's start with something you can hold in your hand. Pick up your phone. The screen you're looking at contains approximately 3 million pixels. Each pixel consists of subpixels that emit red, green, and blue light. Those subpixels are roughly 100 micrometers across, about the width of a human hair. Now we're going to zoom in, and with each step, we'll multiply our magnification by 10. This is called logarithmic scaling, and it's the only way the human mind can traverse the full spectrum of cosmic size without getting lost in the incomprehensible. At 10 times magnification, individual cells become visible. A typical human cell measures about 10 micrometers in diameter. Your body contains approximately 37 trillion cells, each one a bustling metropolis of molecular machinery. The cell membrane, that thin boundary between life and non-life, is only 7 nanometers thick. That's 70 atoms stacked side by side. Everything that makes you alive, everything that separates your organized complexity from the chaos of the external world, depends on a barrier thinner than a soap bubble. Zoom in another factor of 10, and we enter the realm of organelles. The mitochondria, those famous powerhouses of the cell, are typically 1 to 2 micrometers long. Right now, the mitochondria in your body are producing approximately 10 to the 26th molecules of ATP every single day. That's 100 million trillion molecules. Each one stores a tiny packet of chemical energy, and each one exists for less than a minute before being recycled. Your entire energy economy operates on a currency that turns over completely every 60 seconds. The scale of molecular activity happening inside you at this very moment exceeds the number of stars in a million galaxies. Another factor of 10 brings us to individual proteins. Hemoglobin, the molecule that carries oxygen in your blood, measures about 5 nanometers across. Its structure was finally mapped in 1959 by Max Perutz at Cambridge University, after 23 years of painstaking work. When Perutz first saw the complete three-dimensional structure, he wept. Here was a molecule containing 10,000 atoms, folded into a precise shape that had been refined over hundreds of millions of years of evolution. Change just one amino acid in the chain of 574 that make up hemoglobin, and you get sickle cell disease. The difference between health and illness, between life and death, can come down to a single atomic substitution in a molecule 5 billionths of a meter wide. Zoom in again. We're now at the scale of individual atoms, roughly 1/10 of a nanometer. The atoms in your body aren't special. The carbon in your cells, the iron in your blood, the calcium in your bones, these are exactly the same atoms that exist in rocks, in oceans, in distant nebulae. There's no such thing as a living atom versus a dead atom. An iron atom is an iron atom, whether it's in your hemoglobin or in a meteorite. Life isn't a special kind of matter. It's a special arrangement of ordinary matter. You are stardust that learned to think about stardust. But atoms themselves aren't solid objects. Zoom in another factor of 10,000, and we reach the atomic nucleus. If an atom were the size of a football stadium, the nucleus would be a marble at the center of the field. Everything else is empty space, populated only by the probabilistic clouds of electrons. The nucleus itself, containing protons and neutrons, measures about 1 femtometer across. That's 1 quadrillionth of a meter. At this scale, the fundamental forces of nature become visible. The strong nuclear force, 100 times more powerful than electromagnetism, holds the nucleus together against the electromagnetic repulsion of positively charged protons trying to blow it apart. Every atom in your body is a battleground where fundamental forces wage war at energies that would vaporize matter if they weren't perfectly balanced. Go smaller still. Protons and neutrons aren't elementary particles. They're made of quarks, held together by gluons in a quantum dance that physicists are still struggling to fully understand. Quarks have never been observed in isolation. Try to pull them apart, and the energy you invest creates new quarks instead. It's like trying to cut a magnet in half to separate the north and south poles. You just end up with 2 magnets. The scale of quarks represents the smallest distance we can currently probe with our most powerful particle accelerators, roughly 10 to the minus 19 meters. Beyond that, we enter the realm of pure theory. Some physicists believe that at the Planck length, 1.6 times 10 to the minus 35 meters, space itself becomes grainy, pixelated, no longer continuous but discrete. At this scale, quantum fluctuations become so violent that the very geometry of spacetime froths and bubbles like boiling water. Virtual particles pop into existence and annihilate in timeframes so brief that they violate energy conservation without violating the laws of physics. This is the basement of reality, the smallest possible scale, where the word underscore, quote, underscore, 3, underscore has any meaning. We've descended through 43 orders of magnitude from the width of a human hair to reach this point. Now let's reverse direction. Let's zoom out. Start again with your body. You're roughly 1.7 meters tall, give or take. That's our baseline, our reference point, the scale at which conscious experience happens. Zoom out by a factor of 10 and you can see your entire room. Another factor of 10 and your house becomes visible, surrounded by neighboring houses, trees, streets. This is still comfortable territory. Your brain evolved to navigate this scale. You can walk these distances, throw objects across them, judge them intuitively. Zoom out to 1 kilometer and you can see your entire neighborhood. At 10 kilometers, your city becomes visible as an interconnected network of roads and buildings. Human civilization operates primarily at this scale. The average person in a developed country travels about 40 kilometers per day. Our social networks, our economic systems, our political boundaries, all of these emerge from the constraints of distance at the scale of tens to hundreds of kilometers. At 100 kilometers, you can see the curvature of the Earth beginning to emerge. The atmosphere, that thin blue line that contains all the air you've ever breathed, is only about 100 kilometers thick. Above that lies the Kármán line, the official boundary of space. Everything that has ever lived, every human who has ever existed, every war, every love story, every scientific discovery, all of it happened within a layer of gas thinner than the skin on an apple, if the apple were the size of Earth. Zoom out to 1,000 kilometers, and Earth becomes a sphere. From this distance, you can see weather systems swirling across continents. The International Space Station orbits at about 400 kilometers, completing 1 lap around the planet every 90 minutes. Astronauts at this altitude report a profound psychological shift called the overview effect. When you see Earth as a whole, when you watch borders disappear and realize that the atmosphere is a single connected system, something changes in your perception. The tribal boundaries that seem so important on the surface reveal themselves as arbitrary lines drawn on a unified sphere. At 10,000 kilometers, Earth fits comfortably in your field of view. The Moon orbits at 384,000 kilometers, about 30 Earth diameters away. If Earth were a basketball, the Moon would be a tennis ball about 7 meters away. This is the farthest distance any human has ever traveled. The 12 Apollo astronauts who journeyed to the Moon between 1969 and 1972 remain the only humans to have left Earth's immediate gravitational embrace. No one has ventured beyond that tennis ball in over 50 years. Zoom out to 1 million kilometers, and Earth and Moon together become a double-planet system, a pale blue dot accompanied by a smaller gray companion. At this scale, the Sun dominates. Our star sits at 150 million kilometers from Earth, a distance called 1 astronomical unit. Light from the Sun takes 8 minutes and 20 seconds to reach us. When you feel sunlight on your face, you're feeling photons that began their journey before you started reading this sentence. The Sun itself is enormous, 1.4 million kilometers in diameter. You could fit 109 Earths side by side across the Sun's face. Its volume could contain 1.3 million Earths. But here's where our intuition starts to fail completely. Here's where the scale of the universe begins to break our pattern recognition systems. Let's use a different comparison, one that might help your brain grasp what's coming. Imagine the Sun shrunk down to the size of a grain of sand, about 1 millimeter in diameter. At this scale, Earth would be invisible, a speck of dust 1/10 of a millimeter across, orbiting 10 centimeters away from the grain of sand. Jupiter, the largest planet, would be 1/100th of a millimeter wide, orbiting about half a meter from the Sun. Neptune, the outermost planet, would circle at a distance of 3 meters. You could fit the entire solar system comfortably in a small room. Now here's the critical question. At this scale, with the Sun as a grain of sand, how far away is the nearest star? The answer is 4 miles. 4 miles of empty space between one grain of sand and the next. Proxima Centauri, our nearest stellar neighbor, sits 4.2 light-years away. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers per second. That's 9.5 trillion kilometers. Multiply that by 4.2, and you get the distance to the nearest star, 40 trillion kilometers. At the scale where the Sun is a grain of sand, the space between stars is measured in miles of emptiness. This is the true scale of the cosmos. The universe isn't mostly stars and planets with empty space in between. It's mostly empty space with occasional islands of matter separated by distances so vast that light itself takes years to cross them. If you could travel at the speed of a commercial jet, about 900 kilometers per hour, it would take you 5 million years to reach Proxima Centauri. Human civilization has existed for roughly 10,000 years. Agriculture is only 12,000 years old. Writing is 5,000 years old. The entire span of recorded human history would fit into the journey to the nearest star 100 times over. And Proxima Centauri is right next door. Our galaxy, the Milky Way, contains between 100 billion and 400 billion stars. If each star were a grain of sand, you'd need a beach 100 kilometers long and 10 meters deep to hold them all. The Milky Way measures about 100,000 light-years from edge to edge. Light that left the far side of our galaxy when humans were still learning to make stone tools is only now arriving at Earth. We don't see the galaxy as it is. We see it as it was, a fossil record written in light. The Sun orbits the galactic center at about 220 kilometers per second. At this breakneck speed, it takes 230 million years to complete one orbit. The last time Earth was at this exact position in the galaxy, dinosaurs were just beginning to evolve. The Sun has completed only 20 orbits since it formed 4.6 billion years ago. From the galaxy's perspective, our star is young, barely into its adolescence. But the Milky Way is just one galaxy among billions. Zoom out further, and galaxies cluster into groups. Our local group contains about 80 galaxies, dominated by the Milky Way and Andromeda. Andromeda sits 2.5 million light-years away, the most distant object visible to the naked eye. The light you see when you look at Andromeda left that galaxy when the first humans were learning to use tools. You're not seeing Andromeda as it is now, you're seeing its ancient past, a ghost image transmitted across the void. Galaxy clusters form even larger structures called superclusters. Our Laniakea supercluster contains about 100,000 galaxies spread across 520 million light-years. The mass of all these galaxies, all their stars and planets and black holes, creates a gravitational basin that pulls everything toward a central point called the Great Attractor. Our entire galaxy is falling toward this point at 600 kilometers per second, and we won't arrive for another 150 million years. But even superclusters are just threads in a larger cosmic web. When you map the universe at the largest scales, galaxies aren't distributed randomly. They form filaments and sheets surrounding vast voids, like soap bubbles in a foam. The largest known structure, the Hercules Corona Borealis Great Wall, stretches across 10 billion light-years. Light takes longer to cross this single structure than the entire age of Earth. And yet, all of this, every galaxy we can see, every star that has ever been observed, exists within a sphere only 93 billion light-years in diameter. This is the observable universe, the limit of what we can possibly see given the age of the universe and the speed of light. Beyond this horizon, there's more universe, potentially infinite, but its light hasn't had time to reach us yet. We're trapped inside a cosmic bubble, able to observe only the region of space from which light has had time to arrive since the Big Bang 13.8 billion years ago. Think about what this means. The observable universe contains approximately 2 trillion galaxies. Each galaxy contains an average of 100 billion stars. That's 200 billion trillion stars, a number so large that if you counted 1 star per second, it would take you 6 trillion years to count them all. That's 450 times longer than the current age of the universe. And around many of those stars orbit planets. Current estimates suggest there are at least as many planets as stars, possibly more. The number of worlds in the observable universe exceeds the number of grains of sand on all the beaches of Earth. Now let's connect the scales. Let's bridge the gap between the smallest and largest structures in the universe. A quark, the smallest particle we know, measures about 10 to the minus 19 meters. The observable universe measures about 10 to the 27 meters. That's a span of 46 orders of magnitude. If you placed a quark at one end of this spectrum and the observable universe at the other, where would a human being fall on this scale? Almost exactly in the middle. You are the geometric mean between the smallest and largest structures in nature. You're not too big or too small. You're precisely balanced between the quantum and the cosmic. This isn't coincidence. It's a consequence of the fundamental constants of physics. The size of atoms is determined by the electromagnetic force. The size of stars is determined by gravity and nuclear fusion. The size of living organisms is constrained by the strength of chemical bonds and the efficiency of metabolic processes. You couldn't be much smaller without losing the complexity needed for consciousness. You couldn't be much larger without collapsing under your own weight. But here's what makes this truly extraordinary. Those atoms in your body, the ones that are 99.9999996% empty space, they weren't always part of you. Carbon, nitrogen, oxygen, all the elements heavier than helium were forged in the cores of stars. When those stars exhausted their fuel and exploded as supernovae, they scattered these elements across space. Gravity pulled them together into new clouds, which collapsed into new stars and planets. Earth formed from the debris of dead stars 4.6 billion years ago. Life emerged from that stellar material 3.8 billion years ago. And eventually, through billions of years of evolution, that stardust became complex enough to look back at the stars and understand where it came from. You are not in the universe. You are not separate from it, observing it from the outside. You are a temporary pattern in the universe's matter and energy. The atoms in your body will exist long after you die, recycled into new forms, new structures, perhaps eventually new living things. The universe has been around for 13.8 billion years. You'll exist as a conscious entity for perhaps 80 years. That's 6 billionths of cosmic history. You're a brief fluctuation, a momentary eddy in the flow of matter and energy from the Big Bang to the heat death of the universe. And yet, in this brief moment, you are the universe becoming aware of itself. Every second, approximately 1 million atoms in your body are replaced by new ones. You breathe in oxygen molecules that were exhaled by someone in Beijing yesterday. You drink water containing hydrogen atoms that once flowed through the Nile during the reign of Cleopatra. The calcium in your bones was forged in a supernova explosion 5 billion years ago, before Earth existed. Your body isn't a fixed object. It's a pattern of organization that persists even as its constituent parts flow through it like water through a fountain. The quote 4 that exists right now shares almost no atoms with the quote 5 that existed 7 years ago. Yet somehow, the pattern remains. Memory remains. Consciousness remains. This continuity of pattern, despite constant material change, is one of the deepest mysteries in science. Let's examine what happens when we apply the same logarithmic scaling we used for space to the dimension of time. Because the universe doesn't just have a spatial scale, it has a temporal scale equally vast, equally incomprehensible to minds evolved to track the passage of days and seasons. Start with 1 second. That's roughly the duration of a heartbeat, the natural rhythm of human consciousness. In 1 second, light travels 299,792,458 meters. That's far enough to circle Earth 7.5 times. In 1 second, your heart pumps about 70 milliliters of blood through 100,000 kilometers of blood vessels. Your brain processes approximately 11 million bits of sensory information, though only about 40 bits reach conscious awareness. The rest is filtered, discarded, deemed irrelevant by neural networks that evolved to prioritize survival over truth. Zoom out to 10 seconds. This is the timescale of short-term memory, the duration of the psychological present. When you listen to music, your brain integrates sound patterns across roughly 10 seconds to perceive melody and rhythm. Shorter than this, and you hear only disconnected notes. Longer, and the pattern dissolves into abstraction. 10 seconds is the window of, quote, 6 for human consciousness. At 100 seconds, just under 2 minutes, you reach the timescale of basic tasks. Boiling water, reading a page, having a brief conversation. This is still firmly within the realm of direct experience. Your attention can span this duration without effort. 10 minutes. A typical shower. A short commute. The time it takes for light to travel from the Sun to Saturn. At this scale, we're approaching the limits of sustained focus. The human attention span for a single task without distraction averages about 20 minutes. Beyond that, the mind begins to wander, seeking novelty, scanning for threats or opportunities. We're not built for marathon concentration. We're built for vigilance, punctuated by brief periods of intense focus. 1 hour. Approximately 4% of your waking life. In 1 hour, the International Space Station completes 2/3 of an orbit around Earth. A hummingbird's heart beats 250,000 times. A mayfly lives and dies. The scale of an hour is still manageable, still within the scope of planning and anticipation. You can imagine an hour. You can wait through an hour. You can remember what you were doing an hour ago with reasonable clarity. 1 day. 24 hours. Earth completes 1 rotation. This is the fundamental rhythm of terrestrial life, encoded into the circadian clocks of nearly every organism from cyanobacteria to humans. Your body temperature fluctuates by about 1 degree Celsius over the course of a day. Your cognitive performance peaks in late morning and early evening, dips in the early afternoon and late night. These rhythms are so deeply embedded that even in the absence of external time cues, isolated in a cave with no light or clocks, humans naturally settle into a cycle of approximately 24.2 hours. We are creatures of the day-night cycle, synchronized to Earth's rotation by 4 billion years of evolutionary history. 1 week, 7 days. The origin of this unit is astronomical, roughly 1/4 of the lunar cycle, though its cultural significance far exceeds its physical basis. A week is long enough for noticeable change. A wound begins to heal. A habit starts to form. A memory begins to fade. This is the timescale of short-term planning, of work schedules and social routines. 1 month. The Moon completes one orbit around Earth. A human embryo develops from a cluster of cells into a recognizable form with beating heart and budding limbs. This is the timescale where biological processes become visible. Growth, healing, seasonal change. A month is long enough to forget the details of an experience while retaining its emotional resonance. 1 year. Earth completes one orbit around the Sun. This is the fundamental unit of human timekeeping, the cycle of seasons that governed agricultural societies for 10,000 years. In 1 year, your body produces and destroys approximately 98% of its atoms. You are almost entirely new matter, yet you remain yourself. In 1 year, light travels 9.5 trillion kilometers, 1 light year, the distance that gives us our measure of cosmic space. A year is long enough for significant personal change. A child grows noticeably taller. An adult's face shows the first hints of aging. Relationships deepen or dissolve. A year is both intimately familiar and surprisingly substantial. 10 years. A decade. This is the timescale of life chapters. Childhood, adolescence, young adulthood. In 10 years, every atom in your body has been replaced multiple times. The person you were 10 years ago is literally not the same physical entity you are now. Yet memory creates continuity. You remember being that person, even though no material connection remains. In 10 years, the fastest spacecraft humans have ever built, Voyager 1, travels about 2 billion kilometers. It's been traveling for 47 years and has only just left the solar system, entering interstellar space in 2012. At its current speed, it would take 73,000 years to reach Proxima Centauri. 100 years. A human lifetime, give or take. This is the absolute limit of direct human memory. The oldest person alive today can remember events from the early 20th century. But that living connection to the past extends back only about 110 years. Everything before that is history, not memory. In 100 years, the Sun moves about 200 billion kilometers through the galaxy, a distance so vast that light takes 8 days to cross it. Yet this represents only 1/10,000,000th of the Sun's orbit around the galactic center. 1,000 years. A millennium. This is the timescale of civilizations. 1,000 years ago, the Song dynasty ruled China. The Byzantine Empire controlled Constantinople, and the Maya civilization was collapsing in Central America. The English language of 1,000 years ago is barely recognizable to modern speakers. Technology, culture, political systems, all have transformed completely. Yet biologically, humans are identical. A baby born 1,000 years ago, raised in the modern world, would be indistinguishable from any other child. Evolution operates on a much slower timescale than culture. 10,000 years, the span of recorded human history. Agriculture emerged about 12,000 years ago in the Fertile Crescent. Before that, for 290,000 years, anatomically modern humans lived as hunter-gatherers, leaving almost no permanent mark on the planet. In 10,000 years, the Earth's axial tilt changes by about 1/10 of a degree due to gravitational interactions with the Moon and Sun. This tiny shift is enough to alter climate patterns, to turn grasslands into deserts, to raise and lower sea levels. The Sahara Desert was a green savanna 6,000 years ago. It will be green again in another 15,000 years. 100,000 years. Homo sapiens emerged as a distinct species roughly 300,000 years ago. But behaviorally modern humans, with language and symbolic thought, appeared about 100,000 years ago. This is the timescale of human evolution, of genetic change significant enough to alter our biology. In 100,000 years, the constellations shift noticeably. The stars we call the Big Dipper will be unrecognizable. Polaris will no longer be the North Star. The sky itself changes on this timescale, though the change is invisible within a human lifetime. 1,000,000 years, the timescale of species. Most mammal species exist for about 1 to 2 million years before going extinct or evolving into something new. 1,000,000 years ago, Homo erectus walked the earth, using fire and stone tools, but lacking the cognitive sophistication of modern humans. In 1,000,000 years, the sun will be about 1% brighter than it is today, enough to significantly alter Earth's climate. The increased solar radiation will accelerate the weathering of rocks, which removes carbon dioxide from the atmosphere. This will eventually make photosynthesis impossible, killing most plant life. Earth's biosphere has perhaps 1 billion years left before the sun's increasing luminosity sterilizes the planet. 10,000,000 years, the timescale of geological change. 10 million years ago, the Himalayas were still rising, pushed upward by the collision of the Indian and Eurasian tectonic plates. The Mediterranean Sea had not yet formed. Grasslands were spreading across the continents, driving the evolution of grazing animals and the predators that hunted them. In 10 million years, the continents will have moved noticeably. Africa will collide with Europe, closing the Mediterranean. The Atlantic will be wider, the Pacific narrower. The face of the Earth is constantly being reshaped by the slow churning of the mantle beneath the crust. 100 million years. The timescale of major evolutionary transitions. 100 million years ago, dinosaurs dominated the Earth. Flowering plants were just beginning to spread. Mammals were small, nocturnal creatures hiding from reptilian predators. The asteroid that would end the age of dinosaurs was still 35 million years in the future. In 100 million years from now, the sun will be noticeably brighter. Earth's orbit will have changed slightly due to gravitational interactions with other planets. The moon will be about 4,000 kilometers farther away, having gradually receded due to tidal forces. Days will be about 30 minutes longer. 1 billion years. The timescale of planetary evolution. 1 billion years ago, Earth was inhabited only by single-celled organisms. The atmosphere contained almost no oxygen. The continents were barren rock. Complex life, multicellular organisms, would not appear for another 400 million years. In 1 billion years from now, the sun's luminosity will have increased by about 10%. This will trigger a runaway greenhouse effect. The oceans will evaporate. Water vapor in the atmosphere will be broken apart by ultraviolet radiation, and the hydrogen will escape to space. Earth will become a dead world, a second Venus, baked sterile by its own star. Life on Earth has an expiration date, and it's measured in hundreds of millions of years, not billions. 10 billion years, longer than the current age of the universe. In 10 billion years, the sun will have exhausted the hydrogen in its core. It will swell into a red giant, expanding beyond the orbit of Mercury, possibly beyond Venus, perhaps even reaching Earth. The outer layers of the sun will be ejected into space, forming a planetary nebula. The core will collapse into a white dwarf, a dense ember about the size of Earth, but containing half the sun's mass. This white dwarf will slowly cool over trillions of years, eventually becoming a black dwarf, a cold, dark cinder drifting through space. But this won't happen for 10 billion years. The sun is only halfway through its life. We live in the middle of stellar time, just as we live in the middle of spatial scale. 13.8 billion years, the age of the universe. This is as far back as time goes, at least in any conventional sense. Before the Big Bang, the concepts of before and after may not have meaning. Time itself may have begun with the universe. In the first fraction of a second after the Big Bang, the universe expanded from a point smaller than an atom to the size of a grapefruit. This is called inflation, and it happened faster than light, which is allowed because space itself was expanding, not matter moving through space. In the first 3 minutes, protons and neutrons formed and fused into the first atomic nuclei, mostly hydrogen and helium. For the next 380,000 years, the universe was opaque, a hot plasma of particles and radiation. Then it cooled enough for electrons to combine with nuclei, forming the first atoms. Light could finally travel freely. This is the cosmic microwave background radiation we detect today, the afterglow of the Big Bang, stretched by the expansion of space from visible light into microwaves. The first stars formed about 100 million years after the Big Bang. These were massive, short-lived stars made only of hydrogen and helium. They burned hot and fast, fusing lighter elements into heavier ones, then exploded as supernovae, scattering the first carbon, oxygen, and iron into space. Second-generation stars formed from this enriched material, then third-generation stars. Our Sun is at least a third-generation star, possibly fourth or fifth. Every atom in your body, heavier than helium, was created in the core of a star or in the explosion of a supernova. You are made of stellar ash, the waste products of nuclear fusion, recycled and reorganized into a form capable of contemplating its own origin. Now let's connect these temporal scales to the spatial scales we explored earlier. Let's see how time and space interweave to create the structure of reality. Light travels at exactly 299,792,458 meters per second in vacuum. This speed is not arbitrary. It's a fundamental constant of the universe, woven into the structure of space-time itself. Nothing with mass can reach this speed. Nothing without mass can travel slower. Light always moves at exactly this speed, regardless of the motion of the source or observer. This fact, discovered by Albert Einstein in 1905, revolutionized our understanding of space and time. Here's the key insight. Space and time are not separate. They're aspects of a single four-dimensional structure called space-time. When you move through space, you also move through time. The faster you move through space, the slower you move through time, relative to a stationary observer. This is called time dilation, and it's not a theory. It's a measured fact. Atomic clocks on GPS satellites run slightly faster than identical clocks on Earth's surface, because they're moving faster and experiencing weaker gravity. If we didn't correct for this time dilation, GPS navigation would accumulate errors of about 10 kilometers per day. This means that the spatial scales we discussed earlier are also temporal scales. When you look at the Moon, you see it as it was 1.3 seconds ago. When you look at the Sun, you see it as it was 8 minutes and 20 seconds ago. When you look at Proxima Centauri, you see it as it was 4.2 years ago. When you look at the Andromeda Galaxy, you see it as it was 2.5 million years ago. The farther you look into space, the farther you look back in time. The universe is not just vast in space, it's vast in time. And we can see that temporal vastness directly, written in the light from distant objects. The most distant objects we can observe are galaxies whose light has been traveling for over 13 billion years. We see these galaxies as they were when the universe was only a few 100 million years old, when the first stars were just beginning to form. These galaxies no longer exist in the form we observe. They've evolved, merged with other galaxies, perhaps been torn apart by gravitational interactions. We're seeing their ghosts, their ancient light, preserved across billions of years of cosmic expansion. This creates a profound paradox. The observable universe is 93 billion light-years in diameter, but the universe is only 13.8 billion years old. How can we see objects 93 billion light-years away if light has only had 13.8 billion years to travel? The answer is expansion. Space itself is expanding, carrying galaxies apart. A galaxy that emitted light 13 billion years ago was much closer to us then. But in the time it took that light to reach us, space expanded, carrying that galaxy farther away. Today, that galaxy is about 46 billion light-years away, even though its light has only been traveling for 13 billion years. The universe is bigger than its age, multiplied by the speed of light, because space itself is growing. And here's the truly mind-bending part. This expansion is accelerating. Distant galaxies are moving away from us faster and faster. Something called dark energy, which makes up about 68% of the universe's total energy, is pushing space apart. We don't know what dark energy is. We can only observe its effects. In the far future, billions of years from now, this acceleration will carry distant galaxies beyond our cosmic horizon. Their light will be stretched to infinite wavelengths, redshifted into invisibility. Future civilizations, if any exist, will look out at the universe and see only their local group of galaxies. The rest of the cosmos will have disappeared beyond the horizon of observation. They will have no way to know that the universe is larger than what they can see. They will have no way to discover the Big Bang because the evidence will have literally moved beyond reach. We live in a special time, cosmologically speaking. We live in an era when the universe is old enough to have formed complex structures like galaxies and stars and planets, but young enough that we can still observe the distant past. We can still see the cosmic microwave background. We can still detect the signatures of the Big Bang. In 100 billion years, this won't be possible. The universe will have expanded so much that all evidence of its origin will be gone. Future scientists will develop theories of an eternal, static universe, and they'll be wrong. But they'll have no way to know they're wrong. This raises an uncomfortable question. What evidence are we missing? What aspects of the universe have already expanded beyond our ability to observe? The observable universe might be a tiny fraction of the total universe. Some theories suggest the universe is infinite, extending forever in all directions. Other theories suggest it's finite but unbounded, like the surface of a sphere, where you can travel in a straight line forever without reaching an edge. We may never know which is correct. The evidence may be forever beyond our reach, carried away by the expansion of space. But here's what we do know. The universe is comprehensible. Despite its vast scale in space and time, despite the fact that it spans 46 orders of magnitude from quarks to cosmic horizons, despite the fact that it's been evolving for 13.8 billion years, we can understand it. We can measure it. We can predict its behavior. The same laws of physics that govern the fall of an apple on Earth govern the motion of galaxies billions of light-years away. The same quantum mechanics that describes electrons in atoms describes the behavior of particles in the first microseconds after the Big Bang. The universe is not arbitrary. It's structured. It follows rules, and those rules are accessible to human minds. This is perhaps the deepest mystery of all. Why should the universe be comprehensible? Why should the patterns of neural activity in 3 pounds of biological tissue be capable of grasping the structure of reality across 46 orders of magnitude? Evolution shaped our brains to find food, avoid predators, and cooperate with other humans. There's no obvious survival advantage to understanding quantum mechanics or cosmology. Yet we can. The mathematics we invented to describe the world turns out to describe it with shocking precision. The equations of general relativity, developed by Einstein in 1915, predicted the existence of black holes, gravitational waves, and the expansion of the universe, all of which were later confirmed by observation. How did Einstein's brain, evolved to navigate the African savanna, manage to intuit the structure of spacetime? Some physicists argue that the universe is not just comprehensible, but mathematical. That mathematics isn't something we invented to describe reality, but something we discovered, a fundamental aspect of reality itself. In this view, the universe is a mathematical structure, and physical objects are simply patterns within that structure. An electron isn't a tiny ball of matter. It's a pattern of excitation in the quantum field that pervades all of space. A galaxy isn't a collection of stars. It's a solution to the equations of gravity and cosmology. Everything that exists is mathematics made manifest. This is a radical idea, and not all scientists accept it. But it explains why mathematics works so unreasonably well in physics. It explains why the same equations describe phenomena at vastly different scales. It explains why the universe is comprehensible at all. If the universe is fundamentally mathematical, then minds capable of mathematics are capable of understanding the universe. We're not separate observers looking at reality from the outside. We're patterns within reality that have become complex enough to recognize other patterns. You are a pattern, a temporary arrangement of matter and energy that persists for a few decades before dissolving back into the chaos from which it emerged. But during those few decades, you are the universe observing itself. You are stardust that has organized itself into a configuration capable of wonder. Every thought you have, every emotion you feel, every memory you cherish is a pattern of neural activity, which is a pattern of molecular interactions, which is a pattern of atomic forces, which is a pattern of quantum fields. You are patterns all the way down and patterns all the way up. There is no fundamental level where you stop being a pattern and become _9_. There are only patterns, interacting with other patterns, creating new patterns, in an endless dance of complexity emerging from simplicity. And here's the final twist. The pattern that is you is not confined to your body. Your thoughts affect your actions. Your actions affect the world. You leave traces, memories in other minds. Changes in the physical environment. Ripples that propagate outward through space and time. In a very real sense, you are not just your body. You are the sum total of all your effects on the universe. You are the conversations you've had, the ideas you've shared, the objects you've created, the lives you've touched. These effects will outlast your biological existence. They will propagate forward through time, influencing events you'll never witness, shaping a future you'll never see. You are not an isolated pattern. You are a node in a vast network of causality that extends across the entire history of the universe. From this perspective, the question, "How long do I exist?" has no simple answer. Your body exists for decades. Your effects exist for centuries or millennia. The atoms that make up your body exist for billions or trillions of years. The energy that animates those atoms has existed since the Big Bang and will exist until the heat death of the universe. You are not a temporary visitor to the universe. You are a temporary configuration of the universe itself. When you die, you don't leave the universe. You rejoin it, your pattern dissolving into simpler patterns, your complexity redistributed, your information scattered but not destroyed. This is not metaphor. This is physics. The first law of thermodynamics states that energy cannot be created or destroyed, only transformed. The energy in your body right now has always existed and will always exist. It has taken countless forms over the history of the universe. It has been starlight and stellar wind. It has been interstellar gas and planetary rock. It has been ocean water and atmospheric carbon dioxide. It has been grass and grain and the flesh of animals. And for a brief moment, it is you. Then it will be something else. The universe is not a collection of separate things. It is one continuous process, one unbroken flow of matter and energy, temporarily organizing into patterns we call objects, then dissolving and reorganizing into new patterns. You are that process. You are the universe in motion. And for this brief moment, this infinitesimal fraction of cosmic time, the universe has organized itself into a pattern capable of understanding that fact. Here's what nobody tells you about quantum mechanics. It's not weird because we don't understand it. It's weird because we do understand it. And what we understand violates every intuition evolution gave us about how reality works. In 1927, at the Solvay Conference in Brussels, the greatest physicists of the era gathered to debate the implications of quantum theory. Niels Bohr and Albert Einstein engaged in a series of arguments that would define physics for the next century. Einstein insisted that quantum mechanics must be incomplete, that there must be hidden variables we haven't discovered yet, that God does not play dice with the universe. Bohr countered that quantum mechanics is complete, that randomness is fundamental, that the act of observation literally creates reality. The debate was never fully resolved. Einstein died in 1955, still convinced that quantum mechanics was missing something. Bohr died in 1962, confident that the theory was complete. Today, nearly a century later, experiments have sided with Bohr. Reality is stranger than Einstein wanted to believe. Let's examine what this means at the scale of individual particles, then zoom out to see how quantum strangeness connects to the cosmic scales we've explored. Take an electron. According to quantum mechanics, before you measure its position, the electron doesn't have a position. It exists in what's called a superposition, a probabilistic cloud spread across space. The electron is not somewhere we don't know. It is genuinely in multiple places simultaneously. Only when you perform a measurement does the superposition collapse into a definite state. Before measurement, the electron is everywhere it could be. After measurement, the electron is somewhere specific. The act of observation doesn't reveal a pre-existing reality. It creates reality. This isn't philosophy. This is experimentally verified fact. In the famous double-slit experiment, first performed by Thomas Young in 1804 and refined countless times since, you fire electrons one at a time at a barrier with two slits. Behind the barrier is a detection screen. If electrons were simply particles, you'd expect them to pass through one slit or the other and create two bright bands on the screen. But that's not what happens. Instead, you get an interference pattern, alternating bright and dark bands, exactly like the pattern created by waves passing through two slits and interfering with each other. Each electron somehow passes through both slits simultaneously and interferes with itself. Now here's where it gets truly bizarre. If you place a detector at the slits to determine which slit each electron passes through, the interference pattern disappears. The electrons start behaving like particles again, creating two bands instead of many. The act of measurement changes the outcome. It's not that the detector disturbs the electrons. The detector forces them to choose a definite path. Before measurement, the electron takes all possible paths. After measurement, it takes one path. Reality at the quantum scale is fundamentally observer-dependent. This raises an immediate question. What counts as an observer? Does it have to be a conscious human? Can a machine observe? Can a bacterium observe? Where exactly does the quantum world end and the classical world begin? The answer appears to be there is no sharp boundary. Quantum effects don't disappear at large scales. They become increasingly difficult to maintain. This is called decoherence. When a quantum system interacts with its environment, when photons bounce off it, when air molecules collide with it, the superposition rapidly collapses. The larger the object, the more interactions it has with its environment, the faster decoherence occurs. For an electron, superposition can last milliseconds. For a molecule containing thousands of atoms, superposition lasts nanoseconds. For a dust grain, superposition would collapse in less than a trillionth of a second. For a human body, containing 10 to the 28th atoms, maintaining quantum superposition is effectively impossible. But quote 12 is not the same as quote 13. In 2010, a team at the University of California, Santa Barbara created a tiny mechanical resonator, a device about 30 micrometers long, visible to the naked eye, and placed it in a quantum superposition. For a brief moment, this macroscopic object was simultaneously vibrating and not vibrating. The boundary between quantum and classical is not a law of nature. It's a practical limitation based on our ability to isolate systems from environmental interference. This suggests something profound. Quantum mechanics doesn't just apply to small things, it applies to everything. The entire universe is a quantum system. You are a quantum system. Your brain is a quantum system. Every atom in your body exists in superposition until it interacts with other atoms, which causes decoherence so rapidly that the quantum effects average out into classical behavior. But the quantum substrate is always there, underlying everything, even if we can't directly observe it at macroscopic scales. Now let's connect this to consciousness. Your brain contains approximately 86 billion neurons. Each neuron connects to thousands of other neurons through structures called synapses. Each synapse contains millions of molecules. The total number of synaptic connections in your brain exceeds 100 trillion. This network processes information through electrochemical signals, ions flowing across membranes, neurotransmitters binding to receptors, cascades of molecular interactions that somehow give rise to the unified experience you call consciousness. Here's the mystery. How do 100 trillion separate interactions create a single, unified experience? When you look at a red apple, different parts of your brain process color, shape, texture, location. Yet you don't experience these as separate perceptions. You experience one apple. This is called the binding problem, and neuroscience has no complete solution. Somehow, distributed processing across billions of neurons creates integrated consciousness. The whole is not just greater than the sum of its parts. The whole is fundamentally different from the parts. Some physicists and neuroscientists have proposed that quantum mechanics might play a role in consciousness. The idea is controversial, but it goes like this. If consciousness requires the integration of information across the entire brain, and if classical physics only allows local interactions between adjacent neurons, then perhaps quantum entanglement provides the mechanism for non-local integration. Entangled particles share a quantum state instantaneously, regardless of distance. If neurons could maintain quantum entanglement, even briefly, it might explain how distributed processing creates unified experience. The problem is decoherence. The brain is warm, wet, and noisy. Quantum states should collapse almost instantly. In 2014, however, researchers discovered quantum effects in photosynthesis. Plants maintain quantum coherence in light-harvesting molecules for hundreds of femtoseconds, long enough to optimize energy transfer. If evolution found a way to exploit quantum mechanics in photosynthesis, perhaps it also found a way to exploit it in neural processing. The question remains open. We don't know if consciousness is fundamentally quantum or fundamentally classical. We don't even know what consciousness is, really. We only know that it exists because we experience it directly. But here's what we do know. Consciousness, whatever it is the only thing in the universe that can collapse quantum superpositions through observation. A rock doesn't observe. A star doesn't observe. Only conscious systems observe, and only observation creates definite reality from quantum possibility. This means that consciousness is not just a passive witness to the universe, it's an active participant in creating the universe. Think about what this implies at cosmic scales. The universe is 13.8 billion years old. For the first 9 billion years, there was no life anywhere, as far as we know. Stars formed and died, galaxies collided, black holes devoured matter, but there were no observers. According to quantum mechanics, without observers, the universe existed in a vast superposition of all possible states. Every particle was everywhere it could be. Every quantum event took all possible paths simultaneously. The universe was a blur of probability, not a definite reality. Then, about 4 billion years ago on Earth, and possibly earlier on other planets, life emerged. Simple at first, just self-replicating molecules. But over billions of years, life became more complex. Nervous systems evolved, brains evolved, consciousness evolved. And with consciousness came observation. And with observation came the collapse of superposition into definite states. Life didn't just inhabit the universe, life made the universe real. This is called the participatory anthropic principle, proposed by physicist John Wheeler in 1983. Wheeler argued that observers are necessary to bring the universe into existence. Not that consciousness created the Big Bang, but that the universe remained in quantum superposition until observers evolved to collapse that superposition into definite history. In this view, the past is not fixed until it's observed. When you look at light from a distant galaxy, you're not just seeing the past, you're creating the past, collapsing the quantum superposition of all possible histories into one definite history. This sounds insane. It violates our intuition that the past is fixed and the future is open. But quantum mechanics doesn't care about our intuition. In 2007, a team of physicists performed a delayed-choice quantum eraser experiment. They sent photons through a double-slit apparatus, but delayed the decision of whether to measure which slit the photon passed through until after the photon had already hit the detection screen. The result? The choice made after the photon's arrival determined whether it showed particle behavior or wave behavior. The future measurement affected the past behavior. Causality, at the quantum level, can run backward in time. If this is true for individual photons, could it be true for the entire universe? Could the existence of observers in the present affect the quantum state of the universe in the past? Some interpretations of quantum mechanics say yes. The universe's history is not a single definite timeline, but a superposition of all possible timelines. Only observation collapses this superposition into the one timeline we experience. Before observation, all histories exist simultaneously. After observation, one history becomes real. This creates a strange loop. The universe must evolve for billions of years to create observers. But observers are necessary to make the universe's history definite. The universe creates observers, and observers create the universe. Neither can exist without the other. It's like asking which came first, the chicken or the egg. Except the answer is, both came first, because time itself is observer-dependent. Now let's zoom out even further. Let's consider the universe not just as a quantum system, but as a computational system. Because that's what the universe is, fundamentally. It processes information. Every particle interaction is a computation. Every quantum state change is a bit flip. The universe is computing its own future state from its current state, following the laws of physics as its algorithm. How much computation has the universe performed since the Big Bang? In 2002, physicist Seth Lloyd calculated the answer. The universe has performed approximately 10 to the 120 operations on 10 to the 90 bits of information. That's a 1 followed by 120 zeros worth of computational steps. For comparison, the most powerful supercomputer humanity has ever built can perform about 10 to the 18 operations per second. If it ran for the entire age of the universe, it would perform about 10 to the 35 operations total. The universe has performed 10 to the 85 times more computation than all human computers combined could perform if they ran for the age of the cosmos. And what is this computation producing? Complexity, structure, organization. The early universe was nearly uniform, just a hot plasma of particles with tiny density fluctuations. Gravity amplified those fluctuations. Denser regions attracted more matter, becoming denser still. Over millions of years, this process created the cosmic web of galaxies and voids. Over billions of years, it created stars and planets. Over billions more years, on at least one planet and probably many more, it created life. And eventually, it created consciousness. This is the universe computing its way from simplicity to complexity, from uniformity to structure, from randomness to order. And the most complex structure we know of, the most ordered arrangement of matter in the observable universe, is the human brain. Your brain represents the peak of cosmic complexity, the furthest point the universe has reached in its journey from chaos to order. You are not separate from this process. You are this process. You are the universe's computation made conscious. But here's the paradox. The The second law of thermodynamics states that entropy, disorder, always increases. The universe is running down, becoming more random, more chaotic, less organized. How can complexity increase if entropy increases? The answer is that complexity and entropy are not opposites. They can both increase simultaneously. When a star forms from a gas cloud, the star is more ordered than the gas, but the process releases heat, which increases the entropy of the surrounding space. The local decrease in entropy is more than compensated by the global increase. Life does the same thing. You are highly ordered, but you maintain that order by consuming energy and releasing heat, increasing the entropy of your environment. You are a temporary island of order in a sea of increasing chaos. And this is the ultimate fate of the universe. In about 10 to the 100 years, all stars will have burned out. In 10 to the 40 years, all planets will have been ejected from their orbits or fallen into black holes. In 10 to the 65 years, all black holes will have evaporated through Hawking radiation. The universe will be a cold, dark, empty expanse of photons and neutrinos, spread so thin that they almost never interact. Entropy will be at maximum. No structure will remain. No complexity will be possible. The universe will have reached heat death, a state of perfect equilibrium where nothing can ever happen again. But that's trillions upon trillions of years in the future. Right now, we live in the brief window of cosmic time when complexity is possible. When stars shine, when planets orbit, when life exists, when consciousness observes. This window opened about 10 billion years after the Big Bang, when the first stars formed. It will close in about 10 trillion years, when the last stars die. We're about 1,300 billion years into this window. We're near the beginning of the age of complexity, not the end. And here's what makes this moment even more special. We're the first generation of humans to understand this. For all of history until about 100 years ago, humans had no idea how old the universe was, how large it was, what stars were made of, how life evolved. We lived in ignorance of our cosmic context. Now, for the first time, we know where we are in space and time. We know we're on a small planet orbiting an average star in an ordinary galaxy in a universe containing 2 trillion galaxies. We know we're living 13.8 billion years after the Big Bang and trillions of years before heat death. We know we're made of atoms forged in stars and organized by evolution into conscious observers. We know all this because we developed science, a method of systematic observation and experimentation that allows us to transcend the limitations of our evolved intuitions. Science is only 400 years old. Galileo pointed his telescope at Jupiter in 1610. Newton published the Principia in 1687. Darwin published Origin of Species in 1859. Einstein published General Relativity in 1915. Watson and Crick discovered the structure of DNA in 1953. The cosmic microwave background was detected in 1965. The accelerating expansion of the universe was discovered in 1998. We've learned more about the universe in the last century than in all previous human history combined. And the pace is accelerating. In the last 20 years, we've discovered thousands of planets orbiting other stars. We've detected gravitational waves from colliding black holes. We've photographed the event horizon of a supermassive black hole. We've sequenced the human genome. We've created quantum computers. We've begun to understand the neural basis of consciousness. We're living through a golden age of discovery, a time when the universe is revealing its secrets at an unprecedented rate. But here's the uncomfortable truth. We might be alone in experiencing this. The Fermi paradox asks, if the universe is so vast, if there are so many stars and planets, where is everybody? Why haven't we detected any signs of alien civilizations? There are many possible answers. Maybe life is extremely rare. Maybe intelligence is extremely rare. Maybe technological civilizations destroy themselves before they can spread across the galaxy. Maybe they're out there, but too far away to detect. Maybe they're deliberately hiding. Maybe we're looking in the wrong way. Or maybe we're first. Maybe, in this entire galaxy of 400 billion stars, we're the first species to develop technology, to understand physics, to contemplate the cosmos. It seems unlikely. It seems arrogant. But someone has to be first. Some civilization, somewhere in the universe, must be the first to ask these questions. Maybe it's us. If we are first, or even if we're just rare, that places an enormous responsibility on our species. We're not just observers of the universe, we're the universe's way of understanding itself. If we destroy ourselves, if we fail to spread beyond Earth, if we go extinct before we can seed the galaxy with consciousness, then this entire region of space might remain dark and silent for billions of years. The universe will continue to exist, but there will be no one to observe it, no one to collapse its quantum superpositions, no one to transform its mathematical structure into conscious experience. This is why the scale of the universe matters. It's not just an intellectual curiosity. It's not just a collection of impressive numbers. Understanding cosmic scale changes how you see yourself and your place in reality. When you grasp that you're made of atoms forged in stars, that you're a pattern of organization that took 13.8 billion years to evolve, that you're the universe observing itself through conscious matter, it becomes impossible to see yourself as separate from the cosmos. You're not in the universe, you are the universe, temporarily organized into a form capable of self-reflection. And this realization should change how you live. If you're the universe experiencing itself, then every moment of consciousness is precious. Every observation you make, every thought you think, every connection you form with another conscious being is the universe becoming aware of itself in a new way. You're not a passive observer. You're an active participant in the cosmic process of increasing complexity and consciousness. Your choices matter, not just to you, but to the universe itself. This is not mysticism. This is the logical conclusion of everything we've learned about physics, cosmology, and consciousness. You are a temporary fluctuation in the quantum field that pervades all of space. You are a pattern of information processing that emerged from billions of years of evolution. You are a node in the causal network that connects the Big Bang to the heat death of the universe. You are all of these things simultaneously, and understanding this should fill you with both humility and wonder. Humility, because you're infinitesimally small compared to the cosmos, existing for an infinitesimally brief moment in cosmic time. Wonder, because despite your smallness and brevity, you're capable of understanding the universe across 46 orders of magnitude, from quarks to cosmic horizons. You're capable of grasping your own insignificance and finding meaning in it anyway. This is the paradox at the heart of human existence. We're simultaneously insignificant and essential. Insignificant because we're tiny, brief, and fragile. Essential because we're observers. And without observers, the quantum universe remains in superposition, undefined, unreal. We make reality real by observing it. We make the universe meaningful by understanding it. We are the universe's way of knowing itself. And that knowledge comes with responsibility. We're living in a critical moment in cosmic history. We're the first generation to understand our place in the universe. We're possibly the only conscious observers in this entire region of space. What we do in the next few centuries will determine whether consciousness spreads across the galaxy or remains confined to one fragile planet. Whether the universe continues to observe itself through us, or whether this brief experiment in self-awareness ends and the cosmos returns to unconscious existence. The scale of the universe should make you feel small, but it should also make you feel connected. Every atom in your body was once part of a star. Every thought in your mind is the universe thinking about itself. Every moment of your existence is a miracle of complexity emerging from simplicity, of order arising from chaos, of consciousness emerging from unconscious matter. You are not separate from the universe. You are the universe, experiencing itself from one particular perspective for one brief moment in cosmic time. and that moment is now. Let me tell you something that will fundamentally change how you think about knowledge itself. Everything I've told you so far, every fact about atoms and galaxies, every measurement of cosmic scale, every equation describing reality, all of it represents less than 5% of what exists. We know this not through speculation, but through direct observation. When astronomers measure the rotation of galaxies, they find that stars are moving too fast. The visible matter, all the stars and gas we can see, doesn't have enough gravity to hold the galaxy together. It should fly apart. But it doesn't. Something invisible is providing additional gravity. We call it dark matter, and it makes up about 27% of the universe's total mass energy. We have no idea what it is. When cosmologists measure the expansion rate of the universe, they find something even stranger. The expansion is accelerating. Galaxies are moving apart faster and faster. This requires a repulsive force, something pushing space apart. We call it dark energy, and it makes up about 68% of the universe's total mass energy. We have no idea what it is. Add those numbers together. Dark matter, 27%. Dark energy, 68%. That's 95% of the universe, made of things we cannot see, cannot touch, cannot directly detect, and do not understand. Everything we've discussed, every atom in your body, every star in the sky, every galaxy we've observed, all of it is made from the leftover 5%. We are not just ignorant about most of the universe, we are profoundly, fundamentally ignorant. And recognizing this ignorance is not a failure of science. It's science's greatest achievement. Here's why. For most of human history, we didn't know what we didn't know. Ancient civilizations looked at the stars and invented stories. Gods, heroes, cosmic battles. These stories felt complete. They answered every question. Why does the sun rise? A god pulls it across the sky. Why do people die? The gods will it. Why does anything exist? Because the gods created it. These answers were satisfying precisely because they were unfalsifiable. You couldn't prove them wrong, so they felt like knowledge. Science works differently. Science doesn't provide satisfying answers. Science provides testable answers. And when you test them, you often find they're wrong, or incomplete, or only approximately correct under certain conditions. Newton's laws of motion worked perfectly for 200 years, until we discovered they break down at high speeds and strong gravitational fields. Einstein's relativity fixed those problems, until we discovered it breaks down at quantum scales. Quantum mechanics works at small scales. Relativity works at large scales. But they're mathematically incompatible. We know both theories are incomplete. We just don't know how to fix them. This is not a bug in science. This is the feature. Science is the only system of knowledge that explicitly includes "we don't know" as a valid answer. More than that, science actively seeks out the boundaries of knowledge, the places where our theories break down, because that's where new discoveries happen. Every major breakthrough in physics has come from finding something that didn't fit the existing framework. The orbit of Mercury didn't fit Newtonian gravity, which led to general relativity. The spectrum of blackbody radiation didn't fit classical physics, which led to quantum mechanics. The rotation curves of galaxies don't fit our understanding of gravity and matter, which will lead to something new. We just don't know what yet. Let me be more specific about what we don't know. Let's start with the very beginning. The Big Bang Theory describes the universe's evolution from about 1/1,000,000th of a second after the initial singularity. Before that, we have no idea. General relativity predicts that time itself began at the Big Bang, that asking, quote, 15 is like asking, quote, 16. The question is meaningless because there is no, quote, 17 when time doesn't exist. But general relativity breaks down at the extreme densities and temperatures of the Big Bang. We need a theory of quantum gravity to describe what really happened, and we don't have one. Some theories suggest the Big Bang wasn't the beginning, but a transition. Maybe the universe existed before in a different state and underwent a phase change. Maybe our universe is one bubble in an infinite multiverse, constantly spawning new universes through quantum fluctuations. Maybe time is cyclic, and the universe expands and contracts eternally. Maybe the universe is a simulation running on some higher dimensional computer. All of these ideas are mathematically consistent. None of them can currently be tested. We don't know which, if any, is correct. Here's what we do know. The universe is fine-tuned for complexity. The strength of gravity, the mass of the electron, the charge of the proton, dozens of fundamental constants have values that fall within an incredibly narrow range that allows atoms to form, stars to shine, and life to exist. Change any of these constants by even 1% and the universe becomes sterile. Too much gravity, and stars burn out in millions of years instead of billions. Too little, and stars never form at all. Too strong electromagnetic force, and atoms can't bond into molecules. Too weak, and chemistry doesn't work. Why are the constants what they are? We don't know. Maybe there's a deeper theory that predicts these values. Maybe there are infinite universes with different constants, and we exist in one of the rare universes where the constants allow observers to evolve. Maybe a god set the constants deliberately. Maybe it's just luck. We have no way to test these hypotheses. The fine-tuning of the universe is an observed fact. The explanation is unknown. Now let's talk about consciousness, because this is where our ignorance becomes truly profound. You are conscious right now. You're experiencing something. There's something it's like to be you, reading these words, thinking these thoughts. This is called qualia, the subjective quality of experience. The redness of red, the painfulness of pain, the you-ness of you. And we have absolutely no idea how this happens. We know the brain is involved. Damage certain parts of the brain, and consciousness changes or disappears. We can map which brain regions activate during different experiences. We can even predict some of your thoughts by watching your neural activity. But none of this explains why neural activity feels like anything. Why doesn't the brain just process information unconsciously, like a computer? Why is there an inner experience at all? This is called the hard problem of consciousness, formulated by philosopher David Chalmers in 1995. The easy problems of consciousness are things like, how does the brain process visual information? How does memory work? How do we make decisions? These are incredibly complex questions, but they're quote 18 because we know what kind of answer we're looking for. We're looking for mechanisms, neural circuits, information processing algorithms. The hard problem is different. It's not asking how the brain works, it's asking why the brain's work feels like something. Some neuroscientists believe consciousness is an emergent property of complex information processing. When you get enough neurons connected in the right way, consciousness just appears, like wetness emerges from water molecules. Others believe consciousness is fundamental, like mass or charge, a basic property of the universe that we haven't yet learned to measure. Others believe consciousness is quantum mechanical, arising from quantum effects in neural microtubules. Others believe consciousness is an illusion, that there's no real you experiencing anything, just a brain creating the story of a unified self. We don't know which view is correct. We don't even know how to test them. You can't measure consciousness from the outside. You can only experience it from the inside. I know I'm conscious because I experience consciousness directly. I assume you're conscious because you're similar to me. You have a brain like mine, you behave like a conscious being. But I can't prove you're conscious. For all I know, you're a philosophical zombie, a being that acts conscious but has no inner experience. You can't prove I'm conscious either. This is called the problem of other minds, and it's been unsolved for thousands of years. And it gets worse. If we can't even prove other humans are conscious, how do we know where consciousness begins and ends? Is a dog conscious? Probably. A fish? Maybe. An insect? Unclear. A bacterium? Unlikely. A plant? Probably not. A thermostat? Definitely not. But where exactly do you draw the line? What's the minimum requirement for consciousness? We don't know. Some philosophers argue that consciousness might be universal, that every system that processes information has some degree of consciousness. This is called panpsychism. An electron has a tiny amount of consciousness. A rock has more. A brain has vastly more. Consciousness is not something that suddenly appears at a certain level of complexity. It's a fundamental property of matter, present in different degrees everywhere. This sounds crazy, but it's no crazier than the alternative, which is that consciousness somehow emerges from unconscious matter through processes we can't explain. Here's why this matters. If consciousness is fundamental, if it's woven into the fabric of reality like space and time, then the universe has been conscious, in some sense, since the Big Bang. Not conscious like you're conscious, not thinking thoughts or having experiences, but possessing the basic property that, when organized in complex ways, becomes the consciousness you experience. In this view, you're not consciousness appearing in an unconscious universe. You're the universe's consciousness becoming aware of itself through the particular organization of matter that is your brain. But we don't know if this is true. We don't know if consciousness is fundamental or emergent. We don't know if it's quantum or classical. We don't know if it's unique to biological brains or could exist in silicon computers. We don't know if artificial intelligence will ever be truly conscious or just simulate consciousness convincingly. We don't know if consciousness survives death in any form. We don't know if consciousness is the most complex thing in the universe or just one level in an infinite hierarchy of complexity we haven't yet discovered. What we do know is this: consciousness exists. You are proof. And consciousness is the only thing in the universe that can ask questions about the universe. Without consciousness, the universe would still exist, but there would be no one to observe it, no one to measure it, no one to understand it. The universe would be like a tree falling in a forest with no one around. It would happen, but it wouldn't mean anything. Meaning requires consciousness. Purpose requires consciousness. Value requires consciousness. The universe doesn't care if it exists. Stars don't care if they shine. Galaxies don't care if they collide. Only conscious beings care about anything. Only conscious beings can find the universe beautiful or terrible or mysterious. Only conscious beings can ask why. And here's the deepest question we don't know the answer to. Why is there something rather than nothing? This is not a scientific question. Science can tell you how the universe works, but it can't tell you why the universe exists at all. The laws of physics describe what happens, but they don't explain why those laws exist instead of different laws or no laws at all. You can trace causality back to the Big Bang, but you can't explain why there was a Big Bang. You can propose a multiverse, but you can't explain why there's a multiverse. You can invoke quantum fluctuations, but you can't explain why quantum fields exist. Every explanation assumes something already exists. But why does anything exist? Some philosophers argue this question is meaningless, that existence is the default state, and non-existence would require explanation. Others argue that existence is necessary, that a universe with certain properties must exist because non-existence is logically impossible. Others argue that existence is contingent, that the universe could have not existed, and the fact that it does exist is the ultimate mystery. We don't know which view is correct. We may never know. But here's what makes this moment in history unique. We're the first generation to know how much we don't know. Ancient humans didn't know they were ignorant. They had complete explanatory frameworks, mythologies that answered every question. Medieval scholars thought they understood the cosmos, a finite universe with Earth at the center and heaven above. Even 19th century physicists thought they were close to a complete theory of everything. Lord Kelvin famously said in 1900 that physics was essentially complete, with only a few minor details to work out. Those, quote, 20 turned out to be quantum mechanics and relativity, which revolutionized our entire understanding of reality. Now we know better. We know that every answer generates new questions. We know that the more we learn, the more we realize we don't know. We know that the universe is vastly larger, older, and stranger than we imagined. We know that most of the universe is made of things we can't see or understand. We know that consciousness exists, but can't explain how or why. We know that existence itself is a mystery we may never solve. And this knowledge, this awareness of our own ignorance, is liberating. Because it means the universe is not finished revealing itself. It means there are discoveries waiting that will transform our understanding as profoundly as quantum mechanics and relativity did. It means the story of human knowledge is not ending, but accelerating. It means you, right now, are living in a time when the deepest questions about reality are still open, still being explored, still capable of surprising us. Think about what we've learned in just the last century. We discovered the universe is expanding. We discovered quantum mechanics. We discovered DNA. We discovered plate tectonics. We discovered the cosmic microwave background. We discovered exoplanets. We discovered gravitational waves. We discovered the accelerating expansion of the universe. Each of these discoveries was completely unexpected. Each one changed how we see reality. And there's no reason to think we've stopped making such discoveries. In the next century, we might discover what dark matter is. We might develop a theory of quantum gravity. We might detect signs of life on other planets. We might create conscious artificial intelligence. We might upload human minds into computers. We might extend human lifespan indefinitely. We might spread across the solar system, then across the galaxy. Or we might destroy ourselves before any of this happens. We don't know. But here's what we do know. The universe is comprehensible. Despite its vast scale, despite its quantum strangeness, despite the fact that 95% of it is invisible, we can understand it. We can measure it. We can predict its behavior. The human brain, 3 pounds of biological tissue, evolved to find food and avoid predators, is capable of grasping the structure of reality across 46 orders of magnitude. This is astonishing. This should not be possible. But it is. And this suggests something profound. The universe wants to be understood. Not in a conscious, intentional way, but in the sense that the laws of physics are simple enough, elegant enough, mathematical enough, that minds like ours can grasp them. The universe could have been chaotic, random, incomprehensible. But it's not. It follows rules. And those rules are accessible to conscious observers. You are such an observer. You are a pattern of matter and energy that has become complex enough to understand the patterns around it. You are the universe observing itself, measuring itself, trying to comprehend itself. And every time you learn something new about the cosmos, every time you grasp a concept that seemed impossible before, you're participating in the universe's journey toward self-understanding. This is not metaphor. This is literal truth. The atoms in your brain were forged in stars. The energy powering your thoughts came from the sun, which came from the gravitational collapse of a gas cloud, which came from the Big Bang. You are made of the universe. You are not separate from it. And when you think about the universe is thinking about itself through you. So what should you do with this knowledge? How should you live, knowing that you're a temporary pattern in an incomprehensibly vast cosmos, that you're made of stardust, that you're conscious for reasons we don't understand, that you exist in a universe that's 95% mystery? First, embrace the mystery. Don't be afraid of not knowing. The universe is under no obligation to make sense to you. The fact that we understand as much as we do is a miracle. The fact that we can ask questions we can't yet answer is a gift. Curiosity is the most human trait we have. It's what drove us from caves to cities, from superstition to science, from Earth to the moon. Keep asking questions. Keep seeking answers. And when you find that the answers generate more questions, celebrate. That means there's more to discover. Second, recognize your connection to everything. You are not an isolated individual. You are a node in a network of causality that extends across the entire history of the universe. Every breath you take contains atoms that were once part of dinosaurs, oceans, stars. Every thought you think affects the world around you, creating ripples that propagate forward through time. You are not separate from nature. You are nature, temporarily organized into a form capable of self-reflection. Third, take responsibility. If consciousness is rare in the universe, if we're possibly the only observers in this entire region of space, then what we do matters cosmically. The universe has spent 13.8 billion years creating the conditions for consciousness to emerge. Stars had to form and die to create heavy elements. Planets had to form and cool. Life had to evolve for billions of years. All of this happened so that you could exist, right now, reading these words. Don't waste it. Don't squander this brief moment of consciousness. Use it. Create. Learn. Connect with other conscious beings. Leave the universe slightly more complex, slightly more conscious than you found it. Fourth, maintain perspective. Yes, you're cosmically significant as an observer, but you're also cosmically insignificant as an individual. You're one of 8 billion humans on one planet orbiting one star in one galaxy among 2 trillion galaxies. Your problems, your anxieties, your ambitions, all of it is infinitesimally small in cosmic terms. This should be comforting. The universe doesn't care if you fail. It doesn't care if you succeed. It doesn't care if you're happy or sad, rich or poor, famous or forgotten. You're free to define your own meaning, your own purpose, your own values. The universe gives you no script. You write your own. Fifth, look up. Literally. Go outside on a clear night and look at the stars. Remember that you're looking back in time. The light from those stars left them years or centuries or millennia ago. Remember that you're looking at nuclear furnaces millions of times larger than Earth, burning through their fuel, creating the elements that will someday form new planets, new life, new observers. Remember that you're standing on a planet, spinning at 1,000 miles per hour, orbiting a star at 67,000 miles per hour, in a galaxy rotating at 500,000 miles per hour, in a universe expanding at millions of miles per hour. And despite all this motion, you feel still. You feel stable. You feel like the center of your own universe. Because you are. Every observer is the center of their own observable universe. The cosmic microwave background is the same distance from you in all directions. The expansion of space is the same rate in all directions from your perspective. You are not at the geometric center of the universe. There is no such place. But you are at the observational center of your universe. This is true for every conscious being everywhere. We are all centers. We are all edges. We are all connected by the same laws of physics, the same cosmic history, the same fundamental mystery of existence. And here's the final thing you should know. This moment, right now, is unique in cosmic history. The universe is 13.8 billion years old. It will exist for trillions of years more. You exist for perhaps 80 years. That's 6 billionths of cosmic history so far, and an infinitesimal fraction of cosmic future. You are living in the brief window when stars shine, when planets orbit, when life exists, when consciousness observes. Billions of years from now, the universe will be dark, cold, empty. No stars, no planets, no life, no observers. Just photons and neutrinos spreading ever farther apart in an endless void. But that's not now. Now is the age of stars, the age of complexity, the age of consciousness. You are alive during the most interesting period in cosmic history, when the universe is old enough to have created observers, but young enough that there's still something to observe. You are alive during the 1st century, when humans understand their cosmic context, when we know where we came from and where we're going. You are alive during the transition from a single-planet species to a multi-planet species, from biological intelligence to artificial intelligence, from ignorance to understanding. This is not an accident. This is not luck. This is the universe doing what it does, creating complexity, creating consciousness, creating observers capable of understanding their own existence. You are the universe's way of knowing itself. And for this brief moment, this infinitesimal fraction of cosmic time, you have the privilege of being aware of that fact. So use it. Question everything. Learn constantly. Connect deeply. Create meaningfully. Love fiercely. And remember, you are not in the universe. You are not separate from it. You are the universe, experiencing itself from one particular perspective, for one brief moment. And that moment is now. The atoms in your body will exist long after you die. They'll be recycled into soil, into plants, into animals, perhaps eventually into other conscious beings. The energy that animates you will continue to flow through the cosmos, taking new forms, creating new patterns, participating in the universe's endless dance of complexity emerging from simplicity. You are not permanent, but you are not meaningless. You are a temporary fluctuation in the quantum field that pervades all of space, a brief organization of matter and energy into a form capable of wonder. And wonder is the appropriate response to existence. Not certainty, not fear, not despair. Wonder. The universe is vast beyond comprehension, strange beyond imagination, mysterious beyond understanding. And you are part of it. You are made of it. You are it. So look at the stars. Feel the atoms in your body. Think about the 13.8 billion years of cosmic evolution that led to this moment. And recognize that you are the universe becoming aware of itself. That's not poetry. That's physics. That's the literal truth about your existence. You are stardust that learned to think. You are the cosmos observing itself. You are the universe's way of understanding the universe. And for this brief, precious moment, you are here. You are conscious. You are aware. You are alive. Make it count. Remember how we started? Remember those 7 billion atoms working in perfect coordination to create the experience you call, quote, 21. Remember learning that you're 99.999999996% empty space? We've traveled from quarks to cosmic horizons, from femtoseconds to the heat death of the universe, from quantum superposition to galactic superclusters. We've seen that you're the geometric mean between the smallest and largest structures in nature. We've discovered that you're made of atoms forged in stars, that you're the universe observing itself, that consciousness might be the mechanism that collapses quantum superposition into definite reality. But here's what we haven't talked about yet. The edge. Not the edge of the observable universe, we covered that. The edge of understanding itself. The boundary where science ends and philosophy begins. The place where all our equations break down and we're left with nothing but questions that might have no answers. Let's go there now. Let's push to the absolute limit of what we can know, and then peer beyond it into the darkness of what we cannot. Start with this. Why does mathematics work? This seems like a strange question. Mathematics obviously works. We use it to build bridges, launch satellites, predict eclipses, design computers. But why? Why should abstract symbols, manipulated according to arbitrary rules, describe the behavior of physical reality with such unreasonable precision? Eugene Wigner called this, quote, 22 in his famous 1960 essay. He couldn't explain it. Neither can we. Here's the mystery. Mathematics is a human invention. We created numbers, geometry, algebra, calculus. These are tools we built to help us think about the world. But when we apply these invented tools to nature, we discover that nature was already following mathematical rules. The orbit of planets follows equations we can write down. The behavior of light follows equations we can write down. The evolution of quantum states follows equations we can write down. It's as if the universe is made of mathematics, and we're just discovering the equations that were always there. But that can't be right. Mathematics is abstract. It exists in minds, in textbooks, in computer programs. It's not made of atoms. It doesn't have mass or energy. It doesn't exist in space or time. Yet somehow, this abstract system perfectly describes concrete physical reality. How? Some physicists, like Max Tegmark, argue that the universe literally is mathematics, that physical reality is a mathematical structure, and what we call, quote, 23 and, quote, 24 are just patterns within that structure. In this view, an electron isn't a thing that obeys mathematical laws. An electron is a mathematical object, a solution to the Dirac equation, made manifest in physical form. The universe doesn't follow mathematical rules. The universe is mathematical rules, and we're patterns within those rules that have become complex enough to recognize other patterns. This is called the mathematical universe hypothesis, and it's either profound or insane, depending on your perspective. If it's true, then everything that can exist mathematically does exist physically, somewhere in the multiverse. Every logically consistent set of mathematical rules generates a universe. Our universe is just one mathematical structure among infinite others. We exist in this particular structure because it's one of the rare structures that allows observers to evolve. But we don't know if this is true. We can't test it. We can't observe other mathematical universes. We can only observe this one, and marvel at the fact that it's comprehensible at all. Here's another edge: the nature of time. We experience time as flowing from past to future. We remember yesterday, but not tomorrow. We can affect the future, but not the past. Cause precedes effect. This seems obvious, fundamental, built into the structure of reality itself. But physics says otherwise. The equations of physics are time-symmetric. They work equally well running forward or backward. If you filmed a collision between two billiard balls and played the video in reverse, the reversed motion would still obey the laws of physics. There's nothing in the fundamental equations that distinguishes past from future. The arrow of time, the sense that time flows in one direction, doesn't come from the laws of physics. It comes from thermodynamics, from the fact that entropy increases. The future is the direction of increasing disorder. But why does entropy increase? The second law of thermodynamics says it must, but it doesn't explain why. The answer is statistical. There are more disordered states than ordered states, so random changes tend to increase disorder. But this just pushes the question back one level. Why did the universe start in a low entropy state? Why was the Big Bang so ordered, so uniform, so far from thermodynamic equilibrium? If the universe had started in a high entropy state, entropy couldn't increase, and time would have no arrow. The fact that time flows at all depends on the initial conditions of the universe, and we don't know why those initial conditions were what they were. Some physicists argue that time doesn't flow at all, that the past, present, and future all exist simultaneously in a four-dimensional block universe, that the flow of time is an illusion created by consciousness, by the fact that our memories only work in one direction. In this view, your entire life, from birth to death, exists as a fixed structure in space-time. You're not moving through time. You're a four-dimensional object, extended in time just as you're extended in space. And consciousness is simply experiencing different slices of that object sequentially. But we don't know if this is true. We don't know if time is fundamental or emergent. We don't know if the flow of time is real or illusory. We don't know if the past is fixed or if quantum mechanics allows it to change retroactively. We don't know if time had a beginning or if it extends infinitely into the past. We don't know if time will have an end or if it extends infinitely into the future. Time is the most familiar aspect of our experience, and also the most mysterious. Here's another edge: the nature of reality itself. Quantum mechanics tells us that particles don't have definite properties until they're measured. Before measurement, an electron is in a superposition of all possible states. After measurement, it's in one definite state. But what counts as a measurement? What causes the collapse of the wave function? Is it consciousness? Is it interaction with a macroscopic object? Is it decoherence? Or does the wave function never collapse, and instead the universe splits into multiple branches, one for each possible outcome? This is the measurement problem, and it's been unsolved for nearly a century. The Copenhagen interpretation says measurement causes collapse, but doesn't explain what measurement is. The many worlds interpretation says the universe splits, but doesn't explain where the other branches go or why we only experience one. The pilot wave interpretation says particles have definite positions all along, guided by a quantum wave, but requires faster-than-light influences. The objective collapse theories say the wave function collapses spontaneously when systems reach a certain size, but don't explain why that size is special. We don't know which interpretation is correct. We may never know. All of them make the same predictions for every experiment we can perform. They differ only in their metaphysics, in what they say about the nature of reality when no one is looking. And that's not something we can test. This raises a terrifying possibility. Maybe reality doesn't have a nature when no one is looking. Maybe the universe is fundamentally observer-dependent, and asking what it's _quote_25_ independent of observation is a meaningless question. Maybe there is no objective reality, only a collection of subjective observations that happen to be consistent with each other. Maybe the universe is more like a dream than a machine, and consciousness is not something that happens in the universe, but something the universe happens in. But we don't know. We can't know. The nature of reality independent of observation is, by definition, unobservable. We're trapped inside our own observations, unable to step outside and see what's really there. We're like characters in a novel trying to figure out if the world exists when they're not on the page. Here's another edge. The origin of the laws of physics. The universe follows laws. Gravity works the same way everywhere. Light always travels at the same speed. Energy is conserved. These laws are not suggestions. They're not statistical tendencies. They're absolute rules that are never violated. But why? Why does the universe follow laws at all? Why not chaos? Why not randomness? Why not a different set of laws in every region of space? Some physicists argue that the laws of physics are necessary, that they're the only logically consistent set of rules that could govern a universe. Others argue that the laws are contingent, that they could have been different, and we just happen to live in a universe with these particular laws. Others argue that the laws evolved, that the early universe had different laws, and the laws we observe emerged through some kind of cosmic natural selection. Others argue that the laws are arbitrary, chosen by a creator or a programmer or a random quantum fluctuation. We don't know. We can't know. We can't observe other universes with different laws to see if they're possible. We can't rewind the Big Bang and watch the laws emerge. We can't step outside the universe and examine its source code. The laws of physics are the rules of the game we're playing, and we can't stop playing long enough to ask why these rules and not others. And here's the deepest edge of all, the question we started with. Why is there something rather than nothing? Every explanation for the universe's existence assumes something already exists. The Big Bang assumes quantum fields. The multiverse assumes a mechanism for generating universes. The simulation hypothesis assumes a simulator. God assumes a God. But why does anything exist at all? Why is there a quantum field instead of no quantum field? Why is there a multiverse instead of no multiverse? Why is there a simulator instead of no simulator? Why is there a God instead of no God? You can't answer this question by pointing to something that exists, because then you have to explain why that thing exists. You can't answer it by saying existence is necessary, because you have to explain why necessity exists. You can't answer it by saying existence is random, because you have to explain why randomness exists. Every answer assumes existence, and existence is what we're trying to explain. Some philosophers argue that nothingness is impossible, that existence is the default state, that asking why there's something rather than nothing is like asking why 2 + 2 = 4. It just does. It's a necessary truth. But this doesn't feel satisfying. It feels like giving up, like declaring the question unanswerable and moving on. Other philosophers argue that nothingness is possible, that the universe could have not existed, And the fact that it does exist is the ultimate mystery, the one question that will never have an answer. That we're here by pure chance, by an inexplicable quantum fluctuation, by a cosmic accident that had no cause and no reason. That existence is fundamentally absurd, and searching for meaning is futile. But here's what I think. Maybe the question is wrong. Maybe why is the wrong word. Maybe existence doesn't have a reason. Maybe it just is. Maybe the universe doesn't need a cause or a purpose or a justification. Maybe it's enough that it exists, that we exist, that consciousness exists, that we can ask these questions even if we can't answer them. Because here's what we do know. We exist. Right now, in this moment. You are reading these words. You are thinking these thoughts. You are experiencing consciousness. And that experience is not nothing. It's something. It's everything, actually, because it's the only thing you can ever directly know. Everything else, the entire universe, you know only through the filter of your consciousness. You can doubt the existence of atoms and galaxies and quantum fields, but you cannot doubt the existence of your own experience. Cogito ergo sum. I think, therefore I am. This is the one certainty, the one fact that cannot be questioned. And if you exist, if consciousness exists, then existence itself is not nothing. Existence is something, and that something is capable of wonder, of curiosity, of love, of meaning. Not because the universe gave it meaning, but because consciousness creates meaning. You create meaning. Every time you care about something, every time you value something, every time you find something beautiful or terrible or important, you're creating meaning. You're taking the raw material of existence and shaping it into something that matters. This is not a small thing. This is not insignificant. This is the most important thing in the universe. Because without consciousness, nothing would matter. The universe would exist, but it wouldn't mean anything. Stars would shine, but no one would find them beautiful. Galaxies would collide, but no one would find them awesome. Quantum fields would fluctuate, but no one would find them mysterious. Meaning requires consciousness. Purpose requires consciousness. Value requires consciousness. And you are conscious. Right now, in this moment. You are the universe's way of mattering to itself. So here's what I want you to understand. You don't need to know why the universe exists. You don't need to know what consciousness is or where it comes from. You don't need to know if reality is mathematical, or if time is an illusion, or if the wave function collapses. You don't need answers to the deepest questions. You just need to recognize that you're here, that you're conscious, that you're capable of experiencing and understanding and creating meaning. And that's enough. That's more than enough. That's everything. Because in the end, after we've traveled from quarks to cosmic horizons, after we've explored 46 orders of magnitude, after we've confronted the limits of knowledge and peered into the darkness beyond, we come back to where we started. You. Here, now. Conscious. Aware. Alive. Those 7 billion atoms working in perfect coordination. That 99.999999996% empty space somehow creating the experience of solidity. That temporary pattern of matter and energy that will exist for a few decades and then dissolve back into the cosmos. That's you. That's all you. And it's miraculous. Not miraculous in a supernatural sense. Miraculous in the sense that it's statistically improbable, thermodynamically unlikely, evolutionarily contingent. The universe had to be exactly the way it is for you to exist. The constants of physics had to be precisely tuned. The Big Bang had to happen. Stars had to form and die. Planets had to coalesce. Life had to emerge. Evolution had to run for billions of years. Your ancestors had to survive long enough to reproduce. Every single one of them, going back 4 billion years, had to make it. One broken link in that chain, and you wouldn't be here. But you are here. Against all odds, against all probability, you exist. You are the universe's way of experiencing itself. You are stardust that learned to think. You are the cosmos observing itself. You are the answer to 13.8 billion years of cosmic evolution. And what should you do with this knowledge? How should you live knowing all this? Live consciously. Pay attention. Notice the miracle of existence. Feel the atoms in your body. Think about the stars that made them. Look at the night sky and remember that you're looking back in time. Remember that the light from those stars traveled for years or centuries to reach your eyes. Remember that you're standing on a planet spinning through space at thousands of miles per hour, and you feel still. Remember that you're made of the same stuff as those stars, that you're not separate from the universe, but part of it, that you're the universe experiencing itself from one particular perspective. Live curiously. Ask questions. Seek answers. And when you find that the answers generate more questions, celebrate. That means there's more to discover. That means the universe hasn't finished revealing itself. That means you're living in a time when the deepest mysteries are still mysterious, when the most important questions are still open, when the next great discovery could happen tomorrow, or next year, or in your lifetime. Live connected. Recognize that you're not alone. Every other conscious being is also the universe experiencing itself. Every human, every animal, possibly every living thing, is a node in the network of consciousness that spans the planet. When you connect with another conscious being, when you communicate, when you share ideas or emotions or experiences, you're creating something new. You're creating patterns of information that didn't exist before. You're increasing the universe's complexity, its consciousness, its ability to understand itself. Live responsibly. If consciousness is rare, if we're possibly the only observers in this region of space, then what we do matters. The universe spent billions of years creating the conditions for consciousness to emerge. Don't waste it. Don't squander this brief moment of awareness. Use it. Create. Learn. Love. Leave the universe slightly more conscious than you found it. Leave traces that will outlast your body. Leave ideas that will propagate forward through time. Leave the world better than you found it, not because the universe demands it, but because you can, and because it matters to you. Live gratefully. You didn't ask to exist. You didn't earn existence. You didn't deserve existence. You just got lucky. You won the cosmic lottery. You're one of the infinitesimally small fraction of possible arrangements of matter that is conscious, that can experience, that can understand. Be grateful for that. Not grateful to anyone or anything in particular, just grateful. Grateful that you exist. Grateful that you're conscious. Grateful that you can experience this moment, right now, reading these words, thinking these thoughts. And live temporarily, because you will die. Your body will stop functioning. Your consciousness will cease. The pattern that is you will dissolve. The atoms that make up your body will be recycled into other forms. The energy that animates you will flow into other systems. You will rejoin the universe, your temporary organization returning to chaos, your complexity redistributing into simpler forms. But that's okay. That's not tragic. That's just how the universe works. Patterns form and dissolve. Complexity emerges and dissipates. Consciousness appears and disappears. You're not permanent, but you're not meaningless. You're a temporary fluctuation in the quantum field that pervades all of space. You're a brief organization of matter and energy into a form capable of wonder. And for this moment, this infinitesimal fraction of cosmic time, you're here. So be here. Fully, completely, consciously. Don't waste this moment worrying about the past or the future. Don't waste it on regret or anxiety or fear. Don't waste it trying to be somewhere else or someone else. Be here. Be now. Be you. Because this moment is all you have. This moment is all anyone has. The past is gone. The future hasn't arrived. There is only now, only this moment, only this experience of consciousness. And in this moment, you are the universe becoming aware of itself. You are the cosmos observing itself. You are stardust that learned to think. You are 7 billion atoms working in perfect coordination to create the experience you call you. You are 99.999999996% empty space, somehow creating the experience of solidity. You are a pattern that took 13.8 billion years to evolve. You are the answer to the question the universe has been asking since the Big Bang. What am I? You are what the universe is. You are the universe experiencing itself. You are the universe understanding itself. You are the universe mattering to itself. And that's not poetry. That's not metaphor. That's physics. That's the literal truth about your existence. So look at your hands. Feel the atoms in them. Remember that those atoms were forged in stars. Remember that those stars were born from gas clouds that formed from the cooling plasma of the Big Bang. Remember that the Big Bang was the beginning of space and time, the origin of everything that exists. Remember that you are made of that everything, that you are a temporary organization of the universe itself. Look at the sky. See the stars. Remember that you're looking back in time. Remember that the light from those stars left them years or centuries ago. Remember that those stars are nuclear furnaces, fusing hydrogen into helium, creating the elements that will someday form new planets, new life, new observers. Remember that you are made of those elements, that you are the product of stellar alchemy, that you are literally made of stardust. Look at another person. See the consciousness in their eyes. Remember that they are also the universe experiencing itself. Remember that they are also made of stardust. Remember that they are also a temporary pattern that will dissolve. Remember that in this brief moment, you and they are both here, both conscious, both capable of connection. Remember that when you connect with another conscious being, you're creating something new, something that didn't exist before, something that increases the universe's complexity and consciousness. And remember this, the universe is vast beyond comprehension. 46 orders of magnitude from the smallest to the largest. 13.8 billion years old. 2 trillion galaxies. 200 billion trillion stars. More planets than grains of sand on all the beaches of Earth. 95% dark matter and dark energy that we don't understand. Quantum mechanics that violates our intuition. Relativity that warps space and time. Consciousness that we can't explain. Existence itself that we can't justify. But in all that vastness, in all that mystery, in all that incomprehensible scale, there is this. You. Here. Now. Conscious. Aware. Alive. Experiencing this moment. Understanding these words. Thinking these thoughts. Feeling these feelings. And that moment, that experience, that consciousness, is the most important thing in the universe. Because without it, the universe would be nothing. It would exist, but it wouldn't matter. It would be vast, but it wouldn't be meaningful. It would be complex, but it wouldn't be conscious. You make the universe matter. You make it meaningful. You make it conscious. So use this moment, this brief, precious, miraculous moment of consciousness. Use it to experience. Use it to understand. Use it to create. Use it to connect. Use it to love. Use it to wonder. Because this moment is all you have, and this moment is everything. You are the universe experiencing itself, and right now, in this moment, the universe is experiencing you.